Hello everyone. For this lecture we're going to break into a kind of machine learning that, while similar to supervised learning in that it allows you to fit predictive models of materials properties, is really designed with a more rigorous statistical approach that will let you answer questions about how certain you should be in a model's predictions or its parameters in ways that most classes of conventional machine learning algorithms cannot. And these methods, which are known as Bayesian methods, in short let you answer questions like, given some noise in the data I use to fit my model, how certain should I be in the parameters? Or if I have different model forms, neither of which clearly fit the data better than the others, with what certainty should I pick each of these different models? Which one is indeed better for my data, and how confident should I be in that choice? And answering all of these questions boils down to being able to use this mathematical tool called Bayes' rule. So Bayes' rule, in short, lets you understand what the probability of a certain model is with certain parameters after you take your initial guesses of what that should be and update them based on what data you have observed so far. So let's jump into that in a little more detail by starting with the priors and using an example system where we imagine trying to determine whether a coin is fair or not. So my model for this system describes that there are two outcomes with different probabilities, heads or tails, and the relative likelihood of either outcome can be captured by a parameter theta. And I'm going to be very conservative and assume I have no knowledge about what this value of theta should be. It is equally likely to be both perfectly unfair for forming a heads or a tails or anything in between. So this is called a uniform prior. What I'm going to do next is run an experiment of flipping this coin many different times, gathering data about how it performs, D. What I then use with Bayes' rule is I study the probability of having observed that data for certain model parameters in my model form, and that lets me compute the so-called posterior distribution, which tells me how likely my parameters are given the data and model form that I've chosen. So this note here, very similar to my prior, which defines my probability of a certain set of parameters given my choice of model, but now includes the data. So what could happen in this example experiment is I flip this coin enough that I find it's much more likely to assume that this coin is biased towards flipping heads than tails, and it can actually give me an estimate of how confident I should be in that parameter. So I haven't quite ruled out that it is unfair towards tails. So the way that I use this in practice is by solving this integral here, which this is a little bit of a mess, especially unfamiliar if you haven't studied Bayesian methods before. So we'll explain it, each of the terms. So here's the expected value of h, which is some function of your parameters theta, conditioned on observing some certain set of data. So that is to say, what should I expect the value of this function to be given everything that I've seen so far? Now the way that I do that is by computing an average of this function h for certain parameters over all possible parameters, so that's what this d theta tells me, weighted by their probability of observing the data, so that's the posterior distribution. Now this integral here is often impossible to solve exactly or analytically. So the way that one goes about solving this problem is to solve it numerically. And one example of a way you can do that is converting this integral into a sum, where I compute an average. So I've got s points, I average or I sum up all different values of this function h using different parameter s. Now the interesting property of s is that each of these points are drawn from a distribution, or drawn from the posterior distribution. So that means if I were to look at a big histogram of all of the different parameters that I would pole, it would look exactly like this posterior distribution here I developed by solving Bayes' rule. Now, the one thing you might be wondering is, how do I go about finding what that distribution of points is in the first place? And that's where Monte Carlo methods come into play. So Monte Carlo methods are exampled well by this algorithm, Markov chain Monte Carlo, that was invented in the mid-90s. And so how they work is you start out by picking an initial point from your prior distribution. So this could be some reasonable guess of what the parameters should be. Then I generate a new point by, say, adding some random noise to it. And then compute the so-called posterior probability for both this new point and my old one. So this posterior probability has two terms. I first compute the likelihood of this specific set of parameters, or of the data given this certain set of parameters, and how likely this set would be given my prior distribution. Once I have that for both points, I can decide which of those two I'm going to keep based on a probability defined here. So this way I've chosen the probability ensures that as I repeat this choice over time, and this choice is again between deciding whether I'm going to keep my new point or stick with my old one at this loop. As long as I follow this probability distribution, I have a property called detail balance, which means that choice of parameters that I have will follow the probabilities defined by my posterior distribution, which I've identified here. So once I decide with this whether to keep this point with a certain likelihood, I go back and repeat 2, which is either with that new point I created or with the one I started out with, and I repeat the process over and over again. And this, if I run it over time, will trend towards generating samples that come out of this desired posterior distribution. There are actually many different ways of doing this. As I mentioned, this algorithm here was invented in the mid-90s, and there have been a multitude of techniques coming out in the future, or in the future since then, such as combine and multi-nest, which can do this sampling much more efficiently. Won't rely on, or won't generate as many or won't require as many samples to be able to model that distribution very well. Now, once you have this ability to generate samples from your target distribution, you can do a lot of clever things. And these are all by solving different versions of that so-called marginalization integral we described earlier, where I can pick different values of, or different identities for this function h of theta, and be able to extract interesting information like how likely should I expect my model form to be. If I use different models with different sets of parameters, I can compute the expectation value of my probability of having observed my experiments given all of the parameters, and that gives me a way of comparing models. I can see here polynomial order 1 has the greatest marginal likelihood, which means it's probably my best choice. I can also choose h to be my parameter values, and I can compute the average value for my parameters and actually see the full distribution of each of my parameters. Or I could feed them through a functional form, and by sampling many different values of this function, I can get the expected value and the confidence intervals for predictions made using this model. So these are all really powerful tools that let you understand not just which models should work or how much I should trust in their parameters, but I can also use it in helping me make decisions about how much I should trust a particular prediction. And this has a lot of implications in materials science. And we're going to give an example that's captured out of work by Noah Paulson from Argonne National Laboratory, which is based in the area of thermodynamic modeling, particularly CALPHAD, which stands for calculation of phase diagrams. So CALPHAD is a technique that's been around for about 50 years and is based on two key steps. The first of which is describing the thermodynamics of a material based on simple models like this one, where I can describe how stable a liquid is. The mixing enthalpy describes how much energy is released when I mix those two liquids as a function of its composition. So here it's the fraction of rhenium. If I can get a bunch of these thermodynamic functions, I can actually solve using thermodynamics which material or which structures should be stable in a material under different conditions. This chart here shows which materials will be stable at different compositions of rhenium for that same niobium-rhenium alloy. And you can see at some points it's liquid, at some points it's a mixture between a liquid and a crystalline phase, and so on and so forth. So this technique can really help you understand what structures to expect in a material, but it's really based on a lot of empirical data fitting, which has problems. The first of which is the data that I fitted on can have disagreements between different sources of experiments. Additionally, I'm not always sure what model form I should use to describe this data, and there's even noise within each of the experiments that I use. And all of this really raises questions on how much I should trust the model form that comes out of it. And of course, given the subject of our lecture, one route of getting around these issues of certainty is to use Bayesian methods. Now, this is a particularly complicated way to use Bayesian models. So in order to do it, Marius Stan and many of his colleagues over the years have had to develop a few innovations to make it possible in thermodynamics. For instance, they illustrated how you can choose different thermodynamic models to describe each of these properties, such as using this expression to describe the enthalpy, which is again a measure of energetic stability. Additionally, they introduced ways of allowing your Bayesian methods to decide how much you should trust your data. And here we're looking at a likelihood function, which again describes the likelihood of observing a certain set of experimental data, given your parameters for the model itself, and this new parameter alpha, which alpha captures how much trust we should have in a machine learning model, trust we should have within a certain data set, where larger values mean more weight. And in order to make this mathematically possible, you can express this likelihood function as a product over the likelihoods of observing each point of data within each data set, where I weight that likelihood based on my data set certainty term. Additionally, Marius and others have showed how you can be able to fit these machine learning or these Bayesian models to more than one property at a time. We'll note up here that this enthalpy term is related to heat capacity by a derivative as a function of temperature. So if I have data for both heat capacity and enthalpy, I can fit their parameters concurrently by modifying this likelihood function to include a term that describes how well we fit each kind of data. So here are terms that have to deal with how well I fit the enthalpy data, and here are terms which describe how well I fit the heat capacity data. And by doing this, we can bake thermodynamic consistency into our models. I can be able to describe or fit models where my heat capacity and enthalpy terms are guaranteed to be related by the derivative, as we expect from fundamental physics. So given these techniques, you can do a number of useful things and solve many of those problems I highlighted earlier in fitting thermodynamic models. I can use the evidence, which is that Bayes factor, which I described earlier, that method where I look at my probability of observing data given my parameters, and I can use that to pick which model is most likely. Or I can go to each of my parameters and establish confidence intervals in them. Or I could go through and develop a measurement of how much each of my different data sets contributed to fitting this model, and really how much I should trust in using their data. And all of this solves many of those major issues in developing CALPHAD thermodynamic models and allows us to use that technique with much more certainty. And that, I hope, gives a good example of why Bayesian methods can have a lot of use in materials modeling. So to wrap up, the takeaway points that I want you to understand are that Bayesian methods let you combine your initial understanding about what the parameters for some model should be with experimental evidence to be able to produce a distribution called the posterior, which describes the likelihood of different parameters in your model based on what data you've observed thus far. And by generating many different parameters whose probabilities follow this posterior distribution, I can compute a number of useful properties about that model, such as I can take my thermodynamic property models and establish error bounds on different quantities that I derive on them. For instance, this paper from 2003 showed how I can put a confidence interval on the melting temperature for uranium oxide as I add in more beryllium. And further, this really goes on to show how Bayesian methods give you the kinds of confidence intervals backed by robust statistics that are inaccessible to kind of other kinds of machine learning techniques. And there are a lot of subtleties to how I do this properly. As I mentioned, there are advanced algorithms, and there's a lot of work that comes into designing those likelihood functions, like we described, for how Stan and others develop ones that worked well for thermodynamic modeling. And those will be the kind of techniques and tools that we teach you with the practical exercises that go along with this module.